Hello, followers of my YouTube channel. Welcome to today's tutorial. In the last 5 videos, we have seen about modeling with QSWAT in addition to that of uh, manual calibration. And today we will see how to use a SWAT CUP for automatic calibration method. Therefore, today we will see the automatic calibration method. So in order to do this automatic calibration, you should have to open a SWAT CUP. You should have to first install the SWAT CUP. If I showed you here, the SWAT CUP looks like this one. You can download this software freely, as I have told you before in the last SWAT videos from my channel. You can access it. So to do that, first you should have to set up your model, and let me start by clicking new and press next. And you should have to provide text in-out for the SWAT CUP in order to do calibration as well as validation. Alright, so let me open that. Before that, those input-output text in-out file is obtained from our folder under this QSWAT trial one. There is scenario, so you can get from this one. As we have seen before, we have this sim1 before calibration and simulation 2. Yes, as indicated here. So there is text in-out here. So we can we will provide those values in order to do calibration and validation. So let us provide the text in-out from A. Here is QSWAT trial 1, and under this we have scenarios. And let me take the simulation 1 before calibration and select the text in-out from this, say open. So we have now provided that. And the SWAT version for my case is SWAT 2020, 12, and the processor for my laptop is 64-bit, and proceed. And the project type here is should have to select the proper algorithm, yes, which is suitable to your watershed. There are recommended algorithms in different watersheds, so you should have to select the best that is suitable for you. So for my case, Sofito algorithm is the proper algorithm method around lake Anna basin. That is why I'm selecting this. Different researchers are suggesting Sofito algorithm around lake Anna basin. Not only that, on Abai basin areas. So by selecting this, press next, and let me give us the name this QSWAT, yeah, QSWAT SWAT CUP, I can say, and let me provide the place under A and on QSWAT trial. Yes, let me put under this one, and let me finish it. Okay, so it is now extracting our files, and we will see the final SWAT CUP project. Now we have this the project explorer. It contains the reaches, chariots, as well as the subbasins, and mostly we are working with this reach in order to do calibration and validation, as well as sensitivity analysis. Yes, I have prepared one video on what mean sensitivity analysis, what mean calibration and validation. So you can back and see the videos. And in order to do this automatic calibration, should have to provide the calibration input data under this one. So let us provide the parameter information. Yes, actually you should have to review parameters which is highly affects the stream flow or what you want. Yeah, by default there are four parameters from this. Yes, 1 2 3 4. The curve number from minus 0.2 up to 0.2, alpha BF, groundwater delay. Let us use only those four parameters for our tutorial purpose, but you can add other parameters which is related to stream flow from this one, or we can select from those parameters. In addition, we can add new parameters by pressing this add new parameter icon. Yeah, if you say that this add a new parameter, and for instance if you want to add a management parameter, for instance, yeah, for the case of delay practice or the likes, you can get from this one, and you can add parameters. Okay, you can add the parameters. Let me add once for our tutorial harvesting, for instance, the management OP. Let me show you this one. You see, I have added now. If I increase this one, this number 5 is also considered, and you can see under the text view this new parameter. Okay, so you can add in such a way, but for this let us use these four parameters. And the number of parameter here is 1 2 3 4, so you should have to adjust this as 4. And I would like to work on 20 simulations, number of simulations, or let me use 40 simulations, and proceed to the next one. From start the simulation from 1 and end up to 5, but I have ordered 40 simulations, so it will end on 40 simulation. And this file COI is by default extracted one. Yeah, the year starts from 1990, and the last date for the data is also provided, so you can have an access on that. And this file SWAT has different parameters. You can take the parameters from this one as well. Those are the parameters, the soil parameters, the management parameters. This one is the management operation, and also the routing parameters. Yes, the canal channel K effective hydraulic conductivity. This canal N2 means the manganese N value for the main canal and the likes. So you can get those things. Yes, from this SWAT, obsolete SWAT. And in order to add observation data here, you should have to tick, or you should have to expand this observation and click on this observer data. Yeah, so from this, for this tutorial, those are the observed data from 1993 up to that of 1997 for a monthly basis. And we have records of about 62 datas. Yeah, 60 datas. So you should have to copy this one. I think you know that how to prepare this data. Okay, let me show you some highlights. So you should have to provide under this, yeah, under this place, you should have to paste your data. Yes, you should have to paste your data, and the number of data is 60. Yes, 30. Yeah, you should have to provide in such a way. And the flow out here is flow out 1 you can use, or you can rename it. And the number of observed variable is 1, which is stream flow only. And if you add sediment and other parameters, you may increase the number of observed variable. But for now, we have one variable, and which is the stream flow. And actually, for if you have a lot of data for the stream flow, we may separate the data into for calibration, validation, and validation. But now we have only little data, so we cannot separate that. For this tutorial, let us use all of the data at once for the calibration purpose. We have provided the stream flow under this observation, and save your data here. And let me go to this extraction. Under extraction, there is a variable file. We have left the flow out 1, so you should have to delete those, the remaining ones. And the Sofito extraction here is the number of variable to get is 1. Yeah, you should have to give 1. And the variable column is 7, because the stream flow is obtained under column 7 from the database. That is why. And the total number of reach or base in the project is 11. Yeah, 11. And the total number of reach or subbasin to get for the first variable is the number of reach. You see, to get for the first variable is 11, 12. Yeah, I mean we have one this number of reach is 1, and here the reach or subbasin number for the first variable is, we want to measure at subbasin this 12, because this subbasin 12 is at the outlets of our watershed. You see, at the outlets of the watershed, the subbasin number is 11. That is why I'm providing this number under this one. So if you have this, we can remove this one, because we don't have additional parameter. And the beginning year of simulation, not including the warm-up period, is from 1993. Yeah, our stream flow starts from this one, and our stream flow is up to 1997. And let me end of simulation is up to 2000. You can say 2000, or you can use, let me use 1997. Yeah. And the time step here is a monthly time step, so you should have to save this one in such a way. And the objective function here under observation, you should have to provide the number of observed variable is 1. And I would like to measure the performance of our model using the NISAT efficiency if I provide as 5. But if I provide 3, I want to measure using R square and the like. So a percent of bias is for 8 and the like. So you should have to provide. And here you should have to rewrite if you change on the first one. And similarly, you should have to give the stream flow under this. Yeah, the stream flow under this point. Yeah, let me paste this. And you should have to change the number of data here as 60. And the variable file here is 1. Yeah, 1. And you should have to save this one as well, and this one also should be saved in such a way. And no observation is here, nothing is done here. Okay, so we have provided the necessary data under this one, so you should have to calibrate your model by providing such data. So let us see, let us calibrate by clicking on calibrate, and you should have to execute all, yeah, at once. Under this you should have to press Y, yes, that means, and process finish, yeah. So it starts executing or working, so we should have to wait for your outputs in such a way, right? Okay, so the number of simulation is now finished. You can see, you can say that you can click on OK, and say OK here also, and it's now executing our works. Yes, click on OK, and I would like to save as for instance iteration 1, I can say in such a way. Therefore you can expand here, and you can get from the calibration output, you can get the 95 PPU plot in such a way, the 95 PPU plot in such a way, and also the DOT plots, yeah, which parameter is affecting our models and the like. You see the curve number are highly affecting, and those alpha BF is somehow far apart, and the like. The groundwater delay is the second one, and this groundwater QMN is also somehow far apart, and you can actually see the duty plot in such a way. And similarly, you can observe the best simulation here, the best parameters, suggested parameters. uh, we have the fitted values, yes, the minimum value and the maximum value. What we have provided before is there, but here is the suggested value, the best parameter given the best values of objective function of the current iterations. So this is the suggested values, and you can take from this one, and the base simulation is this much observed and simulated. Okay, and you can see the summary statistics from this one. Yeah, the flow out here is the R square is 0.74, the Nash efficiency is 0.69. If you see before, yeah, the R square values is 0.76, yeah, under the visualization, but the Nash efficiency was 0.54. But if you are incorporating those parameters, we have improved the Nash efficiency. And further, you can do also you can do additional calibration methods, I mean additional calibrations, in order to improve your model. Yes, so we can do in such a way, and you can see which parameter is most sensitive, and which parameter is not the most sensitive under global sensitivity, or one at a time. Yeah, this the difference between those two sensitivity method is that the global sensitivity helps us to detect the parameter sensitivity at once, but one at a time means you are checking the sensitivity of the curve number for the initial time, and secondly we may do on the base flow BF factor and the likes. So you should do separately under one at a time sensitivity method. So global sensitivity method is the best one, and you can open this global sensitivity in such a way, and you can see that, you can see from this graph, or from this grid value, the most sensitive parameters are the curve number and alpha BF, because the value which has less than almost less than 0.3 value has high sensitive, or which is greater T stat value is highly sensitive. Therefore, those curve number and alpha BF are the most sensitive parameters. You can observe from this one. So we can do those things in such a way under this automatic calibration method. This one is automatic calibration method. Therefore, in order to do additional calibration, for instance, we have seen this one, and I would like to work or do additional calibration, for instance. So you should have to go to this based calibration and select those parameters. Okay, or you can see that from this one. Yes, proceed to this calibration input and parameter information. You should have to adjust the values. Yeah, for instance, the initial value for our curve number is minus 0.2 up to 0.2, and the recommended one here is this one. The minimum value is this much and the maximum value is this much. Yes, so we have the fitted value between these values, and the alpha BF is from 0 up to 1. Similarly, from 0 up to 1, the fitted value is this much between this value. In the case of groundwater delay, from 30 up to 450, 30 up to 400, and those are the fitted values. But the suggested values, or the suggested uh, values, are this one. This one is the suggested value. Okay, so you should have to copy this one and proceed to this parameter information, and let me paste under this one. And the value for the case of curve number, the initial value is this one. Yeah, up to this one, up to from minus 0.11 up to this one. So you can accept this one because this is less than this one. The suggested maximum value for the curve number is less than this one, and the suggested minimum value is also inside this boundary, so we can accept the value. And the alpha BF, for the case of alpha BF, from 0 up to 1. Yeah, but this value is less than that of this one, so you should have to change this value into 0. Should have to change this value into 0, but you should have to replace 1 by this value. Yeah, copy and paste here. Let me paste and copy this value for the case of curve number and paste here in such a way. In addition, we should have to copy this one and paste here. Yeah, and also you should have to make this 0 for the minimum one, because we should have a boundary. Initially we have a boundary that from 0 up to 1, so this value is less than that of 0, and we should ignore this suggested value. And for the case of groundwater delay, the minimum values is 30 and the maximum is 450, but it is less than that of this one, so you should not accept this range, but you should have to take the maximum value from this one. Yeah, copy and paste under this. Yes, and for the case of groundwater QMN, you should have to take from 0 up to 2, and the minimum value, the suggested minimum value is this one, because it is greater than 0. You can take you should have to change it to the suggested value because it is greater than 0, and the maximum range is this one, and this value is less than 2, and you should have to also change this value by this one. Yeah, you should replace in such a way. So after that you can delete this one, because we have already selected those things, and nothing is new. Yeah, there is no additional thing we can change here. Simply you should have to update the stream flow parameters and save it. So let me calibrate again and see our model performance. Yeah, our model performance in such a way. Yeah, so we should have to wait this calibration, the second calibration. Okay, similarly the second calibration is now finished, and we can get the iteration 2, the output of the calibration 2 in such a way. Let me save as iteration 2, and let us compare the summary statistics between the two calibration methods, because we are working to know the summary statistics. So for the case of iteration 1, the R square value is 0.74, the nice efficiency 0.69, and the likes. And for the case of this calibration 2, R square value 0.73, nice efficiency 0.69, and we can see that the percent of bias for the case of calibration 1 is 21.1, but for this case the percent of bias is now reducing. And you can also compare this p-value and R factors. Yes, because those are the statistical parameters. You see, you should have to work on that. So in such a way, you should have to work on calibration. That means automatic calibration using SWAT CUP in such a way. One thing you should have to take care is when you are passing from calibration 1 to calibration 2, you should have to take care of this. You should have to go to this SWAT CUP. Yes, QSWAT CUP. This is the file name when we are setting our project, and you should have to go to this backup. Yes, under this backup, those are the files. Therefore, when you proceed from one calibration to another calibration, you should have to select all these files and copy this one and back this, and you should have to paste all the uh, backup files at these places in order to proceed to the next calibration, because uh, those uh, previous files are already extracted files, but this backup is the original data, and you should have to work on this. Yeah, in such a way we can proceed the calibration methods, automatic calibrations, in order to get based model for your intended study, okay, intended watershed or your project. Therefore, this is a second way of calibrating our models using SWAT CUP. And I hope this is very interesting and helpful for your work. And I would like to say that if you have any question, you can put under the comment section. I will see that and I will follow or answer your questions. In addition, if you are not subscribing my YouTube channel, don't forget to subscribe and share to your friends. And it is enough for today's tutorial. So have a nice time. Thank you for your time. Bye.